Hi, I'm Swapno, and today is the third session of the path integral series that I'm making. So today I'm going to talk about complex integrals. Okay, I actually spoke of complex integrals in the last session where I did two assignment problems, right? But and there I treated the complex numbers just like real numbers. So I had derived a result involving integrals for real numbers, and I simply substituted those real numbers by complex numbers, and I claim that it works, right? So in today's session, I'm going to give you some motivation of why it works, okay? So let me just get started with a very important identity, which is called Euler's identity, and I'll define integration of complex numbers, all right? So the Euler's identity is given by this expression: e to the ix is cosine x plus I sine x. Okay, so how do you derive this result? So what we will do is that we will use the Taylor expansion to derive this result. So let's say your f of x is cosine x. All right, so I'll write this as a series expansion. Okay, so about x equal to 0. So let's find out f dash x at x equal to 0, which is minus sine x at x equal to 0, which is 0. And if you do f double dash x, then you have to take the derivative of, okay, so I'm doing ddx of cosine x is minus sine x, and then ddx of minus sine x is minus cosine x. Okay, and if you evaluate this at 0, then you get minus 1. So I need all these derivatives, right? I'm doing the Taylor expansion. So I'm going to write f of x is f of 0 plus f dashed x at x equal to 0 times x plus f double dashed x at x equal to 0, x squared over factorial 2, and so on, okay? And f of x is cosine x, right? So I have cosine x is equal to f of 0 is just cosine 0, which is 1. And then the first derivative of f with respect to x is sine x, which when evaluated at 0 gives you 0, so the next term is just 0. And then you take the second derivative, okay, and you get minus 1, and you have 1 over factorial 2 x squared, right? So the series for cosine x is 1 minus, this term is 0. The first non-zero terms involving x is x squared, okay? So x squared over factorial 2, and then if you calculated the next term, you'd have gotten this, and so on, okay? So this is a series expansion of cosine x. All right. So you can find the series expansion of sine x in a very similar way. Okay. So you'll get sine of sine x is x minus x squared over factorial 3 plus x to the power 5 over factorial 5, and so on. Okay. The Taylor expansion of sine would be equal to this, which you can find in a way very similar to the way you found the series expansion of cosine. Okay. All right. So now we're going to use these two results. Okay, the series expansions of sines and cosines, of sine and cosine, to evaluate e to the ix. Okay, so we are going to write the e to the ix in a series form first. Okay, so let's do that. So first, we're going to write e to the x in in terms of the Taylor expansion, just e to the x. There's no complex numbers or anything. Okay. So I'm going to write e to the x is equal to 1 plus x squared over factorial 2 plus x cubed over factorial 3, and so on, right? So we derived this expansion, in the previous, I think in the previous session, or could be the session before that, okay? All right. So now we are simply going to replace x by ix, okay? So e to the ix is going to be 1 plus, in the place of x, you have ix, right? And then you have this, and then ix cubed, okay? So this is 1 plus ix, and this is minus x squared over factorial 2, and this one is, you have I squared, which is negative 1, and then you have an I, okay? So this is minus I x cubed over factorial 3, and so on, okay? So what I'm going to do is that I'm going to collect the real terms, and that will give me this. Okay, I didn't show this, and this term is there somewhere. I didn't write that down, okay? And then the imaginary part would be I times x minus x squared, x cubed over factorial 3. And then if you calculate the next term, then it's x to the 5 over factorial 5, and so on, okay? Now this expression is just cosine x, okay? And that one is just sine x. All right? Okay? And that shows that you have, that shows the Euler identity, right? E to the ix is cosine x plus I sine x. All right? Okay, so now we are in a position to discuss the integral involving complex exponentials, okay, which is what we actually introduced or worked with rather, okay, in the in the last session, okay. So how do you define the integral of a complex exponential? Like how do you write this? Okay, so what I'm going to do is that because I know e to the ix is given by a real part and an imaginary part. Why not simply define the integral of e to the ix as the integral of the real part, okay, plus the integral of the imaginary part, right? Okay, so this thing is going to give us minus sine x, plus sine x, right? Integral of cosine x is sine x, okay, and this one is I times minus cosine x, okay, integral of sine x is minus cosine x, and you have a constant. Always, it's an indefinite integral, so you have a constant always, okay? And, okay, I'm going to erase this. So this is equal to what? You can take minus I as the common factor between the two, and then you will have cosine x plus I sine x plus a constant, okay? So how do I know that this is true? Because let's just multiply minus I, to these two terms. So the first term gives you that, and the second term, you have I times I, which is I squared, which is minus 1 times minus 1 is plus 1, so you get that, okay? Now, notice something interesting. This expression is just minus I times e to the ix plus c, which is also e to the ix over I plus c, right? Okay? Now, if you didn't know the special nature of I, that it's an imaginary number, let's say you just treated it as a constant, okay, just real constant, okay. What would have been the integral of this? It would have been e to the ix over I, right, plus a constant, which is exactly what you get here, okay. But here, you used a definition. You introduced a definition of integrals involving complex numbers first, okay. Okay, but if you did the integral blindly, okay, without knowing anything about complex numbers, you would have gotten the same result, okay? So this is kind of, I'm trying to show you why, you can take a result that you have derived for real numbers and you can use it for complex numbers, in some situations, at least in the problems that we will be doing, okay, in the path integral course, okay? The problems fall in this category, okay? So the results are true for real numbers and for complex numbers, okay? All right? Okay, so let's discuss slightly more on, about these integrals, okay? So let's say you have, so this was an indefinite integral, okay? But suppose you're calculating a definite integral, minus infinity to plus infinity, e to the I x squared dx. So how do you do this integral, e to the I x squared dx? This integral doesn't really converge, right? Because why? Because this is an oscillatory function. You can write this as, using the Euler's identity, you can write this as this plus I times minus infinity, oops, there's an x squared, then sine x squared dx, right? Now these are oscillatory functions, right? I mean, you're integrating from minus infinity to plus infinity. Means that, you'll not get a convergent result, right? But this, if you just use the formula for this integral blindly, then you get a result, right? So let's actually get the result first, okay? So remember this formula, minus infinity to plus infinity, e to the power minus au squared plus bu du, okay, is equal to, let me write it here, is equal to square root of pi over a e to the power b squared over 4a, right? So for this case, b is equal to 0, right? You don't have any term multiplying x. So this is just going to be 1, okay? And then pi over a, square root of pi over a is what? A is negative I, right? If you just compare these two, right? You get a equal to negative I. So your answer is square root of I pi, okay? So I get a result, okay, by using this formula blindly for this integral. So what does it mean? I mean, it doesn't converge. So how can I get a convergent result? Well, what happens is that, you know, in situations like this, you make it convergent, okay? So how do you do that? You multiply an exponentially decaying function, okay? You know, this function is an exponentially decaying, right? It decays exponentially, but it does so very slowly, right? It falls with x very slowly because, why? Because epsilon is a very small number, okay? So that's the kind of game we are playing here. You see, like we're assuming that we're multiplying the actual integrand by a number which is very close to 1, okay? So, you know, you can't quite blame me, right, for doing that because, you know, I'm kind of close to 1, so I'm not doing something which is grossly improper, right? So, okay, so if you do that, however, then you get a convergent integral, okay? So let me just do it here. So I'm going to erase this first, okay? So I'll write, this minus infinity to plus infinity, so this is equal to minus infinity to plus infinity e to the minus, minus x squared epsilon minus I dx. All right, now you have this, this exponentially decaying function, and this converges. So I can, for this one, I can use this formula, right, the one that I wrote here. And what should I get? I get square root of pi divided by a, but in the place of a, I have to write this, okay? And then finally, I have to take epsilon to 0, right? You know, that's the deal because, you know, I introduced epsilon, but I have to take the limit epsilon going towards 0. Otherwise, you know, this will not be very close to 1, right? So if I do that, if I set this to 0, once again I get the same result that I got by using this formula blindly without worrying about, you know, the issues of convergence and so on, all right? So that's the beauty of this formula, okay? So when it converges, this result is actually valid, okay? And to make it converge, we play these tricks, all right? So this happens in physics, you know, a lot of the times, if you get an expression that looks divergent, okay, a physicist asks the question, can we make it convergent somehow, okay? And surprisingly, nature, allows you to do that because the result that you get through this procedure, okay, is used in making predictions, okay, to the real world, and it agrees with the predictions of the, real world, like with an experiment, okay? So anyway, so this process is pretty standard, okay, in physics, right? Okay, so now I'm going to do the last problem for today's session. It's a very important result that's used in path integral formalism. It will be used particularly in deriving Schrodinger equation using the concept of propagator, okay? I mean, it is I think in the 6th chapter or so, all right? So let's derive this result, okay, in the first chapter, because first chapter is about mathematical prerequisites, right? Let's do that. So the result that I'm going to prove involve, the Gaussian functions, and this is the result that I'm going to prove now, and which will prove to be important, okay, for path integral calculations. This is actually used in statistics also a lot, okay, this result, all right? So, all right, so this is the Gaussian distribution, and then you have, this normalizing factor, as they call it, and xy is a variable, okay? And this is equal to sigma squared, okay? So how would you prove that? This is actually, I think, the advanced problem, okay, in the problem set, I believe. Yeah, it's a problem number 3 in additional exercises, all right? So in order to prove that, first we will define an integral which is minus infinity to plus infinity e to the I kx, all right, times e to the minus this thing. Okay, so I have this function, the exponential function, and I'm multiplying this by e to the I kx. Okay, why? Why am I doing that? Okay, how is this going to help us? Okay, how is phi k going to help us? It's going to help us as follows. If you take d phi dk, okay, you're taking the derivative of phi with respect to k. K is this variable, right? So d dk is going to go inside the integral, okay? So you'll have e to the I kx, right, times x squared dx. you see, ddk is here outside the integral, but we took it inside the integral, so we are not questioning the validity of this procedure. Okay, it's we're assuming that it is valid. Okay, which it is. Okay, because this result is true. Okay, so anyway, so we get, if I do ddk of that, then what do I get? Ix, right? E to the ikx, and then I have that. Okay, and if you took the derivative the second time, right? This ikx, once again, you have this e to the ikx, right? This is the only k-dependent term. So if you take another derivative with respect to k, you'll get another ix, okay? So this is what you'll get, all right? So what you have is this ix squared is just, this is minus x squared, okay? Minus x squared times that, okay? Now, notice something very interesting. Let's say you evaluate this at k equal to 0, okay? What do you get? This term, you're setting k to 0, right? So this term is equal to 1, okay? And you have minus x squared, you have that. So this is negative minus infinity to plus infinity, x squared, e to the minus x squared 2 sigma squared dx, okay? So this expression, what you have here is just, this integral, okay? So if I can calculate phi, then I can take the second derivative of phi with respect to k and evaluate that at k equal to 0, okay? That will give me this integral. Okay, and then proving that the result is trivial from that, right? So let's calculate phi k. Can we calculate it? Well, yes, right? Because why? Because this is of this form. Once again, this is this precious formula, right? That we derived in the first session, I believe. E to the minus au squared plus bu du, okay? Which is equal to square root of pi over a e to the power b squared over 4a. Okay, you have to you can actually memorize this this result. Okay, it's Gaussian integral. So for this integral, you can see that a is just 1 over 2 sigma squared, right? A is what multiplies the quadratic term, okay? Which is 1 over 2 sigma squared here, and you have ik, which is b. B is ik. You see, b is an imaginary number here, okay? But it doesn't matter. This formula is valid, okay? For any sets of a and b, all right? Okay, so let's actually evaluate this, all right? So let's do it here, okay? Minus infinity plus infinity. Okay, so a is equal to, let me write this down. A is 1 over 2 sigma squared and b is equal to ik, right? So this integral is going to be square root of pi, right? Divided by a, which is 1 over 2 sigma squared, right? This is a. Okay, and then you have e to the power b squared over 4a. B squared is just minus k squared, right? You square this, you get I squared is negative 1, and you have k squared, and you divide that by 4 times a, which is 4 times 1 over 2 sigma squared, right? So this is 2. So your result is, you can simplify this, and you'll get sigma squared of 2 pi, okay? And then you have e to the power minus sigma squared k squared divided by 2. So this is what you'll have, okay, for phi k. Okay, and then you take the second derivative of this, d2 phi dk squared, right? I mean, it's very straightforward, right? I mean, you have to do derivative of this 2 times, okay? So let me just show you how to do that. I mean, ddk of e to the minus sigma squared k squared over 2. So you have to use the chain rule, right? First you do the derivative with respect to this whole variable, and you get minus sigma squared k squared over 2, and then you take the derivative of this, okay, with respect to k. So what do you get? You get minus sigma squared, I think, right? I mean, ddk of k squared is 2k, so 2 and 2 will cancel out, so you'll be left with that, all right? And then you have to do derivative one more time. Oh, I forgot the k. Okay, all right, yeah, okay, and then, you can do another derivative. I mean, you have to use the product rules and so on. Anyway, okay, so you can do it, and if you do that, then the final result, let me write that down, is going to be, I'm going to write it here, okay. So this is, I mean, this is, by the way, in the book, okay. So sigma cubed square root of 2 pi e to the minus sigma squared k squared over 2, and then you have a multiplying factor which is sigma squared k squared minus 1, okay? And then you set that, you evaluate that to 0, k equal to 0. And if you do that, then this gives you negative 1, so your result is minus sigma cubed square root of 2 pi. Okay? All right? Now remember, this was just negative of this integral, right? We actually showed it previously, right? Just this is exactly equal to the negative of the integral, okay? So now this integral would be just sigma cubed over square root of 2 pi. So, the left-hand side is going to be 1 sigma square root of 2 pi, and this integral is just positive sigma cubed square root of 2 pi, and this is pi, this is not a. Okay, the 2 pi cancels out, and you're going to get sigma squared, which is equal to the right-hand side. Okay, so which is what you have, which is what we had set out to prove. All right. Yeah, so the main idea is to calculate phi k. Okay, and then take the second derivative of that, and then evaluate that second derivative at k equal to 0. That gives you the integral. Okay, and from there you can prove this result. This very important result in both statistics and it's also very important in path integral. Okay, as I said, in deriving Schrodinger equation using the path integral formalism. All right, so that ends today's session, and that also ends chapter 1. Okay, so next time I'll start chapter 2, which is on variational calculus. So I will suggest that you review whatever we covered in chapter 1, like all the exercises and problems we discussed and so on. Okay, so then I will see you in the next video. Thank you for watching.